Okay, this is our screen, our second to last screen that we left off, and then I made up a problem that we said we were going to try to do, but I think I'll skip over that one and just do an actual problem from this section. So, we are looking at second order non-homogeneous differential equations with linear with constant coefficients, and we're looking for where our g function, I think later on I called it f, so let me from the beginning, if you guys are writing these notes, call it f, because that's what that f is going to end up being equal to. So what we want to do is we want to find solutions for this, a particular solution for this, so that we can put it together into a general solution. And we found a way to do this using undetermined coefficients. We found a way to do this when our f function was equal to some nice polynomial or an exponential function or sine and cosine. But if that right-hand side function became more complicated than that, we then were not able to use our technique. So this process is called variation of parameters, and in the book they discuss how it's derived. And then I was reading this just a little bit earlier. So they derive the process for us. And then, wait, they had this to say. So usually it's not a good idea to memorize formulas in lieu of understanding the procedure. However, the foregoing procedure is too long and complicated to use each time we wish to solve the differential equation. In this case, it's more efficient to simply use the formulas and be able to solve for this differential equation. So, that being said, let's not worry about the process. If you are interested in the process of how they derive the formula, it's in the textbook. You can look at it. And in the textbook, it would be page 158, I guess, is the whole process. So back to the formulas that we're going to be using. What we're going to be interested in doing is we're going to be interested in finding the Wronskian for our, well, first we have to find our solution to the homogeneous part. I think, yeah, these are called complementary solutions. We find out those two fundamental solutions for the second order, and then we put those two functions in the Wronskian to get a function that we're going to call W. And then we're going to find W1 and W2. And we're going to take the ratio of W1 over W and then W2 over W. And those will be the new functions that we're going to come up with. And that would be U prime 1 and U prime 2. And we want the original U primes, and then we're going to multiply it by the fundamental solution. And then that would be your particular solution. You'll take that particular solution then, and then add it, tack it on to the complementary solutions, and then we're done. Easy, right? Okay, so that's the process. So let's jump to an actual example here. Let's see, I have a list of examples from the book. We could take a look at the first one. So we're going to find a general solution for this as y double prime plus y is equal to secant x. So secant x is one of those functions. It's not sine or cosine. It's not exponential. It's not a trig or any combinations of those things. So let's see if we can solve for this. So first, let's find our complementary solutions. Let's take a look at the homogeneous differential equation. Let's find our auxiliary equation. Let's solve for that, and we see that we're going to get complex numbers for this, complex conjugates. So the real part is 0, the imaginary part is 1. And so your solution then, y1 is going to be cosine x, y2 is equal to sine x. Okay? Did I do that right? Is that right?
Yep.
So if I went a little too fast, you should really think about this and be comfortable with going from the differential equation to auxiliary equation, finding the roots, and then immediately coming up with the solutions. So if you had complex conjugates as your solutions, then your fundamental solutions will have sine and cosine. And if it was a real solution, that would be e to whatever power it is, and then if it's one real root, then it's e to the power, and then x times e to the power. All right, so from here we're going to do 3 things. First, we're going to find the Wronskian of these 2 functions. So we'll put them here, cosine x, sine x. And the order of this is going to be kind of important because when you define your your W1 and your W2, it's going to be important to place them appropriately. So the first row will be the original functions. The second row will be the derivative. So the derivative of cosine is negative sine x. The derivative of sine is positive cosine x. And the Wronskian tells us to find the determinant of this, which is cosine squared minus negative sine squared. Which is equal to 1. So that's a nice Wronskian. Okay. So the next thing we do is we find 2 more Wronskians. The first one we'll call W1. And for W1, what we're going to do is it's going to be corresponding to the cosine x, the first fundamental solution, which means we're going to knock off this first fundamental solution. We're going to put 0 in for the first slot, and then your f function for the second slot. And then we'll keep the second column the same. That would be sine x and cosine x. Yes? That's just, it just became part of the formula for our process. So for us to get the process down here, this is just a step-by-step process that you'll try to remember. So we found our complementary solution. We found our first Wronskian. And then now we're on our way to find our second and third Wronskian. It's going to be W1 and W2. And then we'll check back on this process as we go along. So this is going to be 0 minus secant x times sine x. And secant is what? Secant is 1 over cosine. So 1 over cosine times sine is sine over cosine. And don't forget that negative sign, so this will be a negative tangent. So that's W1. W2 is going to be the same as W, except we're going to change the second column. So the first column will stay the same. The second column changes to 0 in the f function or the g function. And then the determinant. So this is cosine x times secant x minus negative, and that's 0, so that's not going to matter. Cosine over cosine is 1, so it's another nice function. Yeah, number 1s are usually nice. And when we get to number 10 or 15, then you're all, what happened to the other one? Okay, so now that we got W1 and W2, we are ready to define our function. U1 of x is going to be W1 over W. U1 prime of x. This is prime. We still have to find the original U1, so we still need to take the integral. W1 is negative tan x divided by 1, so that's just negative tangent x. And then if I want the original function, U1, I have to integrate the negative tangent of x. Do we know this? ln of 1 over cosine. The negative outside can be a power. I'll do that in steps. So negative ln of 1 over cosine. Let's worry about the plus c later on. And then the negative sign outside of the ln becomes a power for the argument of the ln. So this is really ln of cosine x. Right on. U2 prime is W2 over W, and that's just equal to 1, isn't it? W2 is 1, W is 1, so U2 is going to be the antiderivative of this, which is just going to be x. So then our particular solution, let's call it yp, should equal to, it's u1 times y1 plus u2 times y2. I should quickly go back over here. So we found the derivatives of u1 and u2, and then now we took the antiderivatives to get the original u1 and u2, and then now we're just going to string them up to find our y sub p, and then once we get that, we'll add it to y sub c. We didn't formally write down y sub c, but that's the last step that we'll take. So yp is going to be u1, which is the ln of cosine x, times y1, which is cosine x, plus y2, which is x, times sine x. Okay? So this, along with the fundamental solutions that we got, will make up our general solution for this differential equation. So y is equal to your arbitrary constant times y1 plus another arbitrary constant times y2 plus the y sub p that we just found, ln cosine x times cosine x plus x sine x, and we are done. Okay? So that's a typical easy problem. It's a process, right? So what are the steps? I have the steps written out there, but I can try to refine it so that we have an easier understanding of this. So, yeah, it's basically here, right? I was just going to put step 1, step 2, step 3, but
Is it written in the book like this, or this is your notes?
these are my notes. I don't know what's written in the book. I mean, aside from what we just copied, right? We just copied. Yeah, it's basically the same thing. First, find the complementary solution. Find the Wronskian. Divide by dividing by A2. We put the equation of the form. I don't know what that means. Find U1 and U2 by integrating the. Yeah, it's basically the same as this, except they just wrote it in the paragraph and I just wrote it line by line. So, same thing. Okay, let's do another one. Number 2. Number 9. Let's do number 9. So this one is y double prime minus 4 is equal to e to the 2x over x. No, we skipped over the annihilator method. So we're not going to cover the annihilator method. This is called variation of parameters. Variation of parameters. All right, so I jump around when I do these notes. I don't know if I should just try to go in order and keep going down. I'll try to do it this way. All right, let's start with step 1. Find the solutions for the homogeneous counterpart. So solutions to y double prime minus 4y is equal to 0. So just ignore the right-hand side or set it equal to 0 and then just find a solution, which we've been doing in section 4.3. And to do that, I'll change my technique or my colors this time. We're going to find the auxiliary equation. So that would be m squared minus 4 is equal to 0. Find the solutions. M is equal to plus and minus 2. And then so you have 2 you're going to have 2 solutions. They're distinct roots, right? So it'll be e to the positive 1 and then times x, and then y2 is going to be e to the negative 2x. So that's step 1. And you can write it as a general solution to this homogeneous differential equation, but we can do that at the end. Okay, step 1, step 2. Find the Wronskian of the 2 solutions that we just got, the 2 fundamental solutions that we just got. So I'll put y1 and y2 there. And now we're going to call this W. So W is equal to, we'll write the functions up on top, e to the 2x e to the negative 2x. And again, it's important to put them in the order that you want them to be presented. You could have done e to the negative 2x first, as long as you're consistent when you're finding your u1 and u2, that's fine. So the derivatives are 2e to the 2x and negative 2e to the negative 2x. When you multiply e to the 2x times e to the negative 2x, what do you get? 1, right? You add the powers. This is 2x minus 2x is 0. E to the 0 is 1. So we got e to the 2x minus 2 e to the negative 2x. Or if you want, I'll just put e to the 0 and I'll get rid of that later. Minus these two things, 2 e to the 0 again, because you're essentially multiplying the same thing. And you get another nice number, that's 4. Okay, so that's step 2. Step 3, we need to find other Wronskians, 2 more Wronskians that will replace the column 1 and column 2. So we need the Wronskian, we'll call it W1, and for W1 I'm going to replace the first column with 0 and the function. There's no easy way to rewrite that. That's e to the 2x over x. And then I'll keep the same column for the second one, e to the negative 2x, 2e to the negative 2x. Oops, negative 2e to the negative 2x. And what is this going to equal to? Well, this is going to be 0 minus, I have e to the 2x over x times e to the negative 2x, and this is going to be 1 over x, negative 1 over x. So that's W1. And then W2 is going to be the same Wronskian, except the second column is going to change. So this is e to the 2x, 2e to the 2x. First column for the original W stays the same, and then the second column is going to be 0, and then the function again, e to the 2x over x. And this time it's going to be e to the 2x times e to the 2x over x, which is going to be what? It looks like e to the 4x over x. So that's step 3. Step 4, I don't know if this is worth a step, but we'll write step 4 here. We'll have u1 prime is going to be w1 over w, and w1 is negative 1 over x, and w is negative 4. So this will be positive 4 over x. What? Should it be 4x? 1 over 4x? 1 over 4x. All right. And we're going to integrate that, so I'll probably take the 1/4 out, and we'll do that in our next step. So our u2 prime is going to be W2 divided by W, which is e to the 4x over x divided by negative 4. So this is going to give us a negative 1/4, negative e to the 4x over 4x. Okay, looking good so far. Step 5, we're going to integrate each of these to get their u's. So this is going to be the integral of negative 1 over 4x. So take the 1/4 out. Integral of 1 over x is what? ln x. So this would be 1/4 ln x. So the antiderivative of this next one, negative 4 negative e to the 4x or 4x. Aside from taking out a negative 1/4, e to the 4x over x and finding the integral of this may not be an easy task. So, any ideas on how to integrate this? U substitution, what would let u equal to? 4x. I don't think that'll work. Parts? So uv, what's u and what's v? Oh, I heard Wolfram. So let's integrate. E raised to the 4x divided by x with respect to x. All right, so x integral EI looks like it's the answer. What that means is that there's no nice closed form answer for this. So the best we can do is leave it the way it is, and maybe we can even just make it look a little bit more formal. We're going to integrate from, I think in the book they use x naught to x depending on what your initial value is. So in this case, we don't have an initial condition, so we'll leave it an arbitrary x naught to x, and then in doing so, you're changing the variable to be x. You guys understanding what I'm saying? And so this will be e to the, I have to change the dummy variable to t or something else that's not x. Et. So I don't have an actual formula for this antiderivative, so we're going to have to leave it as an integral, which is what people do if they want to be exact with things. Otherwise, we can make it look like a series, and we'll have our solution as a series. Oh wait, we'll do that in chapter 6. So for now, this is the best we can do. So this is what U2 is equal to. Should we put stars here and say no closed form integral function or solution? So leave it as a definite integral. So that's step 5. Step 6 would be just to string them up together to get your particular solution. I would probably do step 6 and 7 at the same time. We'll separate it. Step 6, your y particular is going to be u1 times y1. So we have 1/4 ln x, and the y1 that we got was e to the 2x, plus u2 is negative 1/4 integral from x naught to x of e to the 4t over t dt, and then multiply that with y2, which is e to the negative 2x, and then to get our general solution at the very end, we would add our complementary solution, the solutions to the homogeneous, with the C1 and C2, and then add this last one. So our y is equal to C1 e to the 2x plus C2 e to the negative 2x plus the rest of this business, 1/4 ln x times e to the 2x minus 1/4. I'm going to put the e to the 2x first. E to the negative 2x times the integral from your starting point, your initial conditions, e to the 4t over t dt. Okay, that wasn't too bad, aside from this little glitch over here. So I suppose this would be a medium type problem. Okay? All right. Yep. If they give us initial conditions, then we would plug in the x naught, whatever the x naught is here, and then we'll solve for C1 and C2. Yeah. Well, this is a function of x, and so this has to be some other variable inside of the integral. Well, yeah, or du. But if your original differential equation had if this was a t in it, then you can't use a t for the integral. All right, let's take a look at your homework. You only have 5 problems. All right. Pick a number between 1 and 5. I got 3, 4, or 5. 4 or 5? Well, 4, we already have the solutions, right? Five is third order. Oh, let's do 4. Oh, 4 is not a, does not have constant coefficients.
You're at 4.6.
Yeah, we're at 4.6. I don't know what I want to do. We'll probably only have time to do one of them. Yeah. All right, let's do number 5. Yeah, whatever. Oh, since this is a third order, yeah, we're going to have to do 3, but I'm trying to remember what the order is for the W1, W2, and W3. They have it in the book? So just zeros, huh? Oh, yeah. Piece of cake. What if you have non-constant coefficients like the other one? I think you just have to find a particular solution in a particular solution. You could divide it out, the first one, the first term. All right. What are we doing again? Are we doing 4 or 5? 5. Where is it? There it goes. All right. Let's see how we do. So we should expect 3 solutions for the complementary, and then a particular solution will be a long string of things. We'll need Wronskian's W1, W2, W3, which is going to produce a 3x3 matrix, and we have to find the, what's that called? The determinant of a 3x3 matrix. Okay, so we'll go in steps again. Step 1, we got y triple prime minus y prime is equal to 0. Our complementary or auxiliary equation is m cubed minus 1 plus, is it plus 1? Plus m, right? Plus m is equal to 0. And we factor out an m, we're going to get m is equal to 0. And then you got m squared plus 1, which is going to generate a couple of complex numbers. And so our solution, our 3 fundamental solutions for the homogeneous is going to be e to the 0 and e to the I, which is going to generate sines and cosines. So y2 will be cosine x, y3 would be sine x. We're good? Again, this is stuff from section 4.3, and you basically have to know this almost like the back of your hand. Just you gotta be quick on doing this, otherwise this will take time for you to do, which is fine if you need more practice, but you just have to be able to find it quicker. Okay, what was step 2 again? Is it the Wronskian now? So first, our Wronskian W. And I have it in order the way I want it in order here. So this is V1, cosine x, and sine x. Unfortunately, the derivatives of 1 and second derivative is 0. That's going to help in finding our determinant of the matrix. Derivative of cosine is negative sine x. Derivative of negative sine x is negative cosine x, etc. So just take derivatives going down, as many as you need to. Now here's a nice thing about a bunch of zeros in rows or columns is that I can decide to expand along the first column. So I would have 1 times the determinant of a 2 by 2 matrix times negative whatever this number is times the determinant of the other matrix that's left, the submatrices. But since they're all 0, I don't have to worry about those things, which is nice. Okay? Now, it's not that it's a shortcut. It's just that if you have 2 of the things in a row or a column are zeros, then you're going to choose to expand on that particular row. So basically, you have 1 times the determinant of the submatrix plus 0 times some other determinant plus another 0 times some other determinant, which we don't need to write anymore because they're zeros. Yeah? No. Or which columns you mean? Because they're going down in the column. So yeah, if I switch the order of these things, then my things would be switched, and it doesn't. No, the answer is no. It doesn't matter where you put the y1, y2, y3. As long as now that I put y1 first, and that's the number 1, and then y2 and y3 are in these rows, then I'll have to remember that when I find my w1, w2, and w3. All right, so we got nice sine and cosine, which is going to give us, I think, a constant. So positive sine squared and minus negative cosine squared. So I'll just put 1. Sine squared, cosine squared. So step 3, we're going to need to find 3 Wronskians. And what we're going to do is we're going to fill in whatever column we're going to fill in with 0, 0, and cotangent, because that's our function. So for the first one, I'm going to replace 1, 0, 0 with 0, 0, and cotangent. And we got cosine x minus sine x minus cosine x, sine, cosine, negative sine. Pretty much, let's just be careful, yeah. So cotangent, and then you cross this out, and then you take the determinant of that submatrix. And you should, in this case, it doesn't matter, but you should remember that if you're expanding along a row or a column, this is a plus, this is a minus, this is a plus. The sign changes. So technically, I would have plus 0 times some determinant of some matrix, minus 0 times another determinant of another matrix, and then I'll get this last one, plus cotangent times the determinant of this submatrix. And this is going to be another sine squared plus cosine squared business, so that's going to leave us with a cotangent. Okay? So for W2, the first one stays the same. Now the column, the second column, since we're talking about the 2, will be 0, 0 cotangent. And the last column will be sine, cosine, and minus sine. Now here, since I have a couple of rows, or I got a bunch of options to take, so let me select a weird one. Let's expand along this, and I'm just doing this to entertain myself. It's probably easiest to expand on the first row or first column, but I'm going to choose the second row just to show you how the determinant expansion works. So each of these elements and submatrices will have a sign, and so if I always start with the upper left-hand corner. So this sign for this 0 is going to be negative. The sign for the second 0 is going to be positive. The sign for this 0 is going to be negative. So those are my signs. If I decide to expand on the second row, which is what I'm doing here, I'm going to get a negative 0 times the determinant of something that I don't care about. But if you do care, it'd be 0 sine, cotangent, negative sine. And then my second one will be plus 0 times the determinant of another matrix that I don't care about because it's going to get multiplied by 0. And then the last one would be a negative cotangent. Nope, sorry, cosine. So negative cosine of x, and if I take a look at that, if I'm expanding on that, I would cross out that row and that column, and what do I have left as a submatrix? The submatrix I have left is 1, 0, 0, cotangent. And had you expanded a different way, we should still get the same results. I don't know if any one of you guys decide to expand a different way, but if you expanded a different way, we should still get the same results. So I have a negative cosine x, and the determinant of this is 1 times cotangent. I don't know if it's worth writing as sine over sine or cotangent. It would be cosine over sine, so that would be cosine squared over sine. I don't think it's worth rewriting until we need to later on. Okay, so that's W2. W3 is 1, 0, 0. I'll keep the second column as cosine x minus sine x minus cosine x. And then the last column will change to 0, 0 cotangent. Again, expanding any way you want. And the easiest way, which is what I should have done for the second one, but the easier way, I think, to expand this is to expand along the first row. So the other two are going to be 0, so the only thing that's going to matter is that first one, which has a plus. So it'll be 1 times the determinant of minus sine x, 0 minus cosine x, cotangent x. And that is equal to negative sine x times cotangent x minus 0. All right. And since w is just equal to a constant 1, our u1, u2, and u3 would just be w1, w2, and w3. So I'll do that as step 4. Or not u, but u1 prime, u2 prime, and u3 prime. Okay, so we need to take the antiderivative of each of those and see what happens next. Good so far? Is that good or is that what? Hands up in the air kind of thing. Well, this is being recorded, and I'm sure you can go to YouTube and find all kinds of other variation of parameter examples. Wait, variation of parameters, right? We got step 4 over there, so step 5 would be integrating a whole bunch of, or 3 functions. This is u1 prime, so we need u1 is going to be the antiderivative of cotangent x. Anybody got this off the top of their heads? You say it with so much confidence. Oh, sorry, it's just... Yeah, but W is equal to 1. If you guys are going to say negative ln of something, that's not going to help me. Negative ln of what? Ln sign? All right. Negative ln of sign? What happened?
Wait, what did we integrate?
Oh, thanks. There you go. So positive ln sine x. U2 is going to be the integral of negative cosine x cotangent x. So if you're tutoring Calc 2, this is where you would give them an example problem. So here, integrate this. And sit there and watch them struggle and wait for the answer. Right? That's what I used to do. No? Oh, wait, that's what I do to you guys. Okay. Integrate. Where are we? Integrate negative cosine x times cotangent x with respect to x. Oh, that's not too bad. Actually, you'd probably find a nicer formula. Here they went to half angle, which means this was extended or expanded somehow. See if I can put this together. Nope. The sine and the cosine here becomes a cotangent, right? There'll be the ln of this thing minus ln of this thing is going to be ln of a quotient. So just to simplify it just a tad bit, I would go ln of cotangent is cosine over sine, right? So why don't I just write that? So it starts off with a negative cosine x plus ln of cotangent x over 2.
This is our ln inside ln.
Oh, yeah. Yeah, ln of cosine. No. They're out there.
Oh yeah, so the brackets, there's brackets here and then the bracket here. So the cosine over sine can go as a quotient. This can be done by hand, by the way. You know, cotangent is cosine over sine, so you have cosine squared over sine squared, and you can split that up, and it'll be fun if you do it by hand. The third one is the antiderivative of minus sine x times cotangent x, which will probably be similar. So let's see what similar thing we get.
Is this one is cosine x should be tangent and cotangent. Cotangent is cosine over sine, so the sine x cancel with the sine x. Will be minus cosine x, and the antiderivative will be sine x only.
For which one?
For the last one.
Oh, for that, yeah. So we didn't even, I didn't even have to do this, but I'm writing it down anyway. So yeah, good job. So this is yeah. So the signs will cancel. You just have negative cosine x antiderivative of that. Yeah, good. Okay. All right, we're practically.
Sine x, not minus. Sine x.
Was it? All right, so we do need Mathematica, huh? I got negative sine x, so I'm going to go with that. Yeah, so there's a negative out here. Right. Okay. So now that we got these things, we just couple them up with a y1, y2, and y3, the 1, the cosine, and the sine. And then, so I'm going to jump straight into step 7. So step 6 would be your y particular is equal to just these things, right? Multiplied by the y1s. Should I do this step? No. Okay. So step 7 is our final answer. So our final answer is going to be a constant times y1 plus a constant times y2, which is the cosine, plus a constant times y3, which is a sine, plus the y particular, which is u1 times y1, and remember the y1 is the one next to the c1, so this is just going to be the ln of sine x plus u2 times y2, and y2 is cosine x, so this would be minus cosine x plus ln of the cotangent of x over 2 times y2, which is cosine, plus u3, which is negative sine, times sine also. So negative sine squared. And the sine is important. The SIGN, sine, is important for the sine, SINE. So the sign for the sine is important, is what I was trying to say. And that's our answer. Suppose we should check our answer. It's going to take us 5 minutes to type it in, right? Have you guys gotten comfortable typing stuff in here and doing things quickly? No. All right. Assuming we're going to use capital C1. You use subscripts here? If you press shift and underscore, you get that subscript kind of quickly. Cosine x plus c, oops, shift and underscore, 3 sine x. All right, so that's the complementary solution. Now let's try to get the general solution here. Do you use absolute value?
Yes.
Okay. Sine x. So I'm going to go with what I have here, which is a plus and then a negative inside of a parentheses. cosine x plus ln. Oh, I hope this works because Mathematica simplified it for us. Cotangent of x over 2 oops. Close that parentheses, multiply by cosine x. And then minus, I'll simplify this one, minus sine squared x. Do you use the power here? All right. This is where we hold our breath and make sure, hopefully we get the right answer. Can't tell. Still in suspense?
The x has to be
You think?
the x has to
I don't know if that should make a difference.
Wait, isn't C1 e to the
E to the 0. It's e to the 0.
but e, it's what's this one? No, okay, perfect.
ln cotangent. Let's see.
We practice in revision and see how the answer actually, like the syntax of the answer.
We're going to leave this? If I practice another version, can I come back to the same problem? Oh.
Sometimes just the syntax.
Show answer? Show answer?
Yeah.
So this is what you guys do, huh?
Alright,
So this... Oh, they use tangent. So I have a feeling it's this middle one. Wait, they lost one. They could have combined something here. No.
maybe it's that confusion with the negative sign.
Well, I have a feeling it's that cotangent. Let me go back to Mathematica and do this integral again. There's a way to expand this, and so I'm assuming the questionable call here is the expansion of the cotangent. Let's see, what section is this? 4-6? Yeah, so this is the issue in the middle here.
And there's no sine squared.
And there is no sine squared.
So then that other sign is positive to it.
Which one?
That one. Because it would be negative sign, but then you take then you take the integral of that.
But it would be negative. Yeah, it was.
It was negative cosine, and then the derivative of cosine is negative sign. You get to negative.
But the antiderivative is positive sign.
Yeah.
So I think this is still okay.
They have the ln time. One that has a sign is ln.
Oh, well, let's see. There's this. I think it's this business, because this is what happens. You got cosine and cosine. It's cosine squared. And then this is minus sine squared. So that's how they got rid of the other term. And so it's back to this business over here, how this is supposed to be equal to it is multiplied by cosine, right? In the solution, it is multiplied by cosine. No, it's multiplied by sine. Oh, that's the tangent. Yeah, it's multiplied by cosine. So apparently, let me do one more check here to actually prove that our answer is correct. The log of cosecant of x minus cotangent of x, is that equal to log of cotangent x over 2? Wait, true or false? Oh, well, whatever. I have a feeling that if you take the cotangent of x over 2 and expand it, it's going to equal to this somehow, and which is going to give us the same result. So that's what I think it is. You guys taking pictures of the answer. All right, so we're done. I'd say that was correct.